In physics, any arrangement of two isolated conductors carrying equal and opposite charges, a positive Q and a negative Q, is classified as a capacitor. The measure of this system is its capacitance, denoted by the letter C. We define this metric strictly as the ratio of the stored charge, Q, to the potential difference, V, that exists between those two conductors. As these notes show, we measure this ratio in farads. A system has a capacitance of exactly 1 farad when it stores 1 coulomb of charge for every 1 volt of potential difference across the gap. Looking at this relationship, it is easy to assume that capacitance changes when the charge or voltage changes. It does not. The value C is a fixed constant for any given physical arrangement. It is entirely independent of the electrical variables Q and V. A capacitor's defining trait is not the current amount of charge it happens to hold at any moment. It is the physical structure's inherent capacity to maintain an electrical potential. In practical engineering, the primary objective is straightforward. We want to store a massive amount of charge, Q, while keeping the overall potential difference, V, as small as possible. When the potential difference gets incredibly high, it generates a severely strong electric field in the space immediately surrounding the conductors. This note details a hard environmental limit. If the electric field becomes too strong, it rips electrons off surrounding air molecules. Air normally acts as an insulator, but past its dielectric strength, 3 million volts per meter, it ionizes, causing stored charge to leak away. When voltage exceeds these environmental limits, the insulation fails. The charge violently bridges the gap as a spark, destroying the system's stored potential. Because we are strictly bound by the breakdown voltage of the surrounding environment, we cannot simply pump infinite voltage into a system. To store more charge safely, we must physically re-engineer the capacitor to have a naturally higher baseline capacitance. To calculate how to increase that baseline, physicists rely on the standard parallel plate model. This specific geometry isolates 2 primary physical variables, the total area of the plates and the exact distance separating them. This diagram illustrates a real-world complication at the boundaries of these plates. The electric field is not perfectly uniform all the way across. At the finite outer edges, the field lines bow outward, creating an uneven fringing effect. To calculate the internal properties accurately, we apply a mathematical boundary condition. We establish that the square of the distance between the plates must be vastly smaller than their total area. This specific assumption renders the messy fringing edges mathematically insignificant. It gives us permission to treat the internal electric field as perfectly uniform, setting up a precise derivation. Looking at this internal gap, the electric field is strictly defined by the surface charge density over the vacuum permittivity constant. Since surface charge density is just the total charge divided by the area, we can rewrite the electric field as Q over epsilon naught times area. We find the overall potential difference across the entire vacuum gap by multiplying that field by the physical distance between the plates. As shown in the final boxed equation here, substituting this expanded definition of voltage back into our foundational capacitance ratio cancels out the charge entirely. This leaves us with a final formula. Capacitance equals epsilon naught times area divided by distance. The math proves an absolute physical reality. In a vacuum, a capacitor's strength relies on 0 electrical variables. It is purely a function of geometric area and distance. We can push this geometric limit further by introducing a third physical variable, a solid dielectric block with a specific thickness and a known dielectric constant inserted directly into the vacuum. This diagram demonstrates the physical mechanism of polarization. The external field from the plates forces the molecular dipoles within the solid block to align, which creates bound surface charges on the outside faces of the dielectric material. These bound charges generate a secondary internal counterfield. Because this new vector directly opposes the original external field, the total net electric field inside the material drops significantly. The top equation calculates the new total potential difference. We simply sum the voltage drop across the empty vacuum region and add it to the voltage drop across the weaker dielectric-filled region. Factoring this split voltage back into our capacitance formula mathematically shrinks the denominator, resulting in this generalized equation for a system utilizing a single dielectric. Dielectrics do not add extra charge to the system. They increase total capacitance strictly by generating internal counterfields. Physically, this behaves exactly as if we had shrunk the electrical distance between the plates, allowing them to hold more charge before reaching the environmental breakdown voltage. We can scale this physical mechanism. Instead of a single uniform block, we can engineer a gap filled with multiple distinct layers of different materials, each possessing its own thickness and specific dielectric constant. As detailed in this expanded fraction, the denominator simply expands linearly. We subtract the physical thickness of every individual layer from the total distance, and then systematically add back their respective dielectric modified terms. Regardless of the internal complexity or the sheer number of distinct materials used, the system's total ability to store electrical energy is fully predictable. It remains an additive sum of physical and material geometry. The top right diagram tests the first extreme boundary condition, expanding the dielectric material until its thickness exactly matches the total distance, completely filling the gap. When distance and thickness match exactly, they cancel out. A full-space dielectric simply acts as a pure direct multiplier to the baseline vacuum capacitance. The ultimate test is substituting our insulating dielectric with a highly conductive solid metal plate. A perfect metal essentially has an infinite dielectric constant. This infinite denominator reduces the internal field term to absolute zero, nullifying the electric field inside the block. The final math reduces to a simple subtraction of the metal's thickness from the total distance. Mathematically and physically, inserting a solid metallic block is completely identical to simply moving the original outer plates closer together. Testing these extreme limits confirms the absolute rule of the system. Capacitance is strictly and solely an architecture of space and material.